So our second unit in Gen Chem 2 is going to be on properties of mixtures. So a lot of what we learned about in our first unit is going to have application here, particularly with regards to intermolecular forces. So 3 lectures on this, and just to give you a heads up of where this is going, our first lecture is very qualitative, thinking about solutions, solubility of substances, and then thinking about what we call a solution cycle. So how do we actually have things go into solution? The second skill is going to be largely quantitative in dealing with how do we determine concentrations of substances, and then qualitatively thinking about why that matters with an introduction to colligative properties. Our third skill, and this is going to be the skill that you're going to have your in-person quiz on, is going to be doing colligative property calculations. So talking specifically about boiling point elevation, freezing point depression, vapor pressure effects, so how we affect vapor pressure lowering, and then thinking about creating or generating osmotic pressure. So that's kind of where we're going. So again, our first skill here is on solutions, solubility, and the solution process. So how we're going to make solutions. So a lot of qualitative stuff just to introduce you to some of the language that's going to be important for this unit. So some D and S words that we need to think about. So I'm just going to read through these, kind of highlight the important pieces here. We're talking about forming solutions. Solutions are formed when you mix solvent and solute. So a solute is usually the substance that's present in smaller amounts. So solvent is usually more abundant. That's how we define those. So even thinking about mixing things like ethanol and water, whatever is present in larger amount is considered to be the solvent. What happens when we form a solution is we say that the solute is solvated or surrounded by solvent molecules. So make sure that you're familiar with these terms so we can understand and think about what's happening when we form a solution. We're going to talk a lot about solubility, and solubility has to do with the maximum amount that dissolves in a fixed quantity of solvent at a given temperature. As we'll see when we get to the end of this unit, that there is a temperature dependence that we're going to see with solubility. 2 D words that are important, and it's really important that you understand the distinction between these 2 D words. A substance dissolves when there are more favorable interactions between the solvent and the solute than exist with the solute and the solvent independently. We're going to talk about this like a friend's analogy. You have 2 solutes interacting over here. You've got 2 solvents interacting over here. When we form a solution, what happens is we have new interactions between solute and solvent. So what has to happen is we break those old friend interactions and we're going to make new friend interactions. Okay? When we dissolve something, the new friend interactions are more energetically favorable than the old interactions. We kind of go downhill in energy. That's a big theme for things that we're going to see. Now, we're going to use as an example sugar, table sugar, which is a covalent compound, and then table salt, sodium chloride. Those are different. We've got a covalent compound with sugar. We've got an ionic compound with salt. An important D word to distinguish is dissociation. We only use dissociation when we're talking about ionic compounds, and that refers to kind of breaking those ionic bonds, those ionic interactions, and separating ions in solution. So both sugar and salt dissolve in water, but only salt dissociates. Okay, a lot of D and S words that are important that we make sure we understand. One other piece of information to kind of highlight, when we're talking about this dissolution process, this is a physical change, okay? You can get back the original solute if you just evaporate the solvent. If you can't obtain back that original solute, a chemical change happened. We had a reaction that occurred. Just as an example here, we've got hydrochloric acid that we've got here, and we've got solid zinc. So here's our chemical equation for what I'm going to talk about here. When you mix these 2 together, we actually have redox chemistry happen. We learned about that last semester. And what happens is you start generating zinc ions in solution, zinc 2+, and then chloride ions in solution, Cl-. Okay? So what happens is we initially get an aqueous solution of zinc chloride, but if you evaporate off all of this water, you'll be left with green crystals, which are zinc chloride. That's a different substance than the zinc metal and the hydrochloric acid than you started out with. So this was a chemical reaction, not a dissolution process. Even though we ended up with a salt that dissolved in water, that's a dissolution process. The idea of this initial first step was a chemical process. And that's different from what we're talking about in this learning unit. Okay, so when we make solutions, we're going to kind of do some qualitative explaining of how and why solutions form. When we make solutions, we can explain what happens by talking about intermolecular forces. So again, that's how we tie in our unit from Unit 1 there. And we can think about this in terms of like dissolves like, right? We talked about intermolecular forces. So if we've got things that have similar intermolecular forces, a polar solvent and a polar solute, they're going to dissolve one another. And that's why a salt, which is an ionic compound, dissolves in water, which is a polar compound. And if we look at a molecular level about what happens when salt dissolves, and truly when we're talking about a salt, it dissociates. What happens is we are going to take water molecules and have them surround these ions. Okay, so that's this dissolution process. We are solvating these ions. That happens favorably because we've got polar water molecules interacting with charged ions. So we can think about this just from the simple intermolecular force standpoint, but we can also explain it with energetics. So I need to make sure to do a little review here to make sure that some terms that were introduced in Gen Chem 1 are still up here. We want to talk about enthalpy and entropy. All right, enthalpy has the letter H. Here's what I want you to think about when you hear enthalpy. Think about heat. I want you to envision bonds and intermolecular forces, and things that are favorable, things that have favorable enthalpy, release heat, or make bonds and intermolecular forces. That's favorable enthalpy. Entropy has the letter S. When you think about entropy, I want you to think about disorder and the phrase more molecules moving more. So things that are favorable from an entropy standpoint have molecules moving around more, or we have more molecules that we've made in a process. So we're going to use both enthalpy and entropy from an energy standpoint to explain why some solutions form. It's all coming down to a cost-benefit analysis. Remember when we had our friends sort of analogy here? If we're going to make a new solution and we've got solvent and solute, when we have these two pure solute and solvent, the only interactions that we have are solute molecules for other solute molecules and solvent molecules for other solvent molecules. So what needs to happen to make a solution are three things. We need to break solvent-solvent interactions, break solute-solute interactions, and then make new solvent-solute interactions. So that's what we have here in sort of this equation, this enthalpy equation. This is sort of like Hess's law where we're adding up enthalpies. The delta H for the overall process has to do with the cost of breaking solute-solute interactions, the cost of breaking solvent-solvent interactions, and then the gain that we have when we form those new interactions. And at the end of the day, if these costs are more than compensated for by the gains, then we have a solution that will be formed. We can use that energy sort of analogy to explain that. Just highlighting here, if you ever see this here, delta H of hydration, this has to do with a specific sort of dissolution process where the solvent is water. Okay, so let's look at a couple of pictures to explain this. If we had something that was exothermic, that meant there was extra heat after our process was done, extra energy that was given off as heat. So let's look at this picture here. Here we've got a solvent and a solute that we're going to try to mix together. We just talked about it being costs to separate solvent particles from each other and solute particles with each other. Now remember, this is not what physically happens. This is a thought exercise to have us think about the energetics of this process. We've got to separate old friends in solvent and solute, and then when we mix them together, we're going to have new interactions form. Now in this case, when we add up the two costs, this is the net of the two costs right there. This is the gain. And in this example, Our gains are bigger than our costs, so the extra energy is given off as heat in solution. And we'd say that this process is exothermic. Let's look at the flip side. What if we had a situation where our costs, the cost of separating solvent particles and separating solute particles, was larger and could not be compensated for by the enthalpy of putting them back together? In that case, our solution would actually get cold because it would have to pull in extra energy from the environment in order for this process to happen. We'd say that this process is endothermic. Okay, so we can have both of those situations, but this one seems a little bit odd because it seems like we're going uphill. Okay, so we'll talk about that in a little bit. This has practical applications too. I know a lot of you have commented that you like having sort of a practical application here. Two practical applications are how a heat pack works and how a cold pack works. If you've ever had one of those, portable kind of heat or cold packs, you ever notice that if you shake it, you can hear like that there's salt inside, and then there's like a bag that's inside that you have to puncture and mix that stuff together. What you're actually doing is mixing a salt in water that either pulls in heat from the surroundings to make a cold pack or adds heat to the surroundings to make a heat pack. And here are the two salts that are commonly found that allow us to do that. So real interesting kind of practical application. Usually something that's fun to do as a demo in class, but just can't do that right now. All right, last thing to talk about is when we think about solubility, I want you to think about this being what we call an equilibrium. Introducing this term early and often here is important because we're going to have 3 whole units that are devoted to equilibrium. We talked about equilibrium in our last unit when we talked about vapor pressure. Remember when we talked about a bottle of water that was sitting out, and eventually you'd see water condense on the top of that bottle because water molecules were simultaneously escaping from the liquid phase into the gas phase, but then also kind of going back into the liquid phase. And we would reach a certain vapor pressure of water, a certain concentration of water molecules in the gas phase after a certain amount of time. And so that idea of molecules kind of going into the gas phase and coming back to the liquid phase created what we call a dynamic equilibrium. Well, the same can be true here when we talk about putting a salt in water, dissolving and dissociating a salt in water. So again, says here, when a solid is dissolving at the same rate as the dissolved particles are recrystallizing. So again, we're using the dissolve term because this could apply to sugar as well. What's going to happen is the concentration of salt or sugar, in that case, would remain constant in solution and would reach what we call an equilibrium at constant temperature. Okay? We're going to say that this solution then is saturated. It has as much solute in solution as possible. Now we do know that there's a temperature dependence to this, right? You know, and think about this, if you want to dissolve sugar in water, it dissolves much better in hot tea than it does in cold tea. So some great practical examples to think about this. A few more S words to think about. When we talk about a saturated solution, there's a maximum amount of solute that we can get in at a given temperature. Again, noting this temperature dependence. We can take a solution that doesn't have as much solute as you might think it would have, and that's an unsaturated solution. But really interestingly, we can create what's called a supersaturated solution. And I'm going to have a fun video to share with you to kind of highlight a supersaturated solution. By adding heat, we can actually put more solute in solution than we normally would have. And then when that solution cools, as long as that salt doesn't crash out of solution, we've created a supersaturated solution. And as I'll show you with this video, you can do some really fun things with that. All right, last thing to think about, and then there's one little qualitative or quantitative piece with this first unit, is thinking about how we can affect solubility. I've already given you kind of a primer for this. We can affect solubility with temperature. Most solids become more soluble at higher temperatures. And again, with that tea analogy, it's much easier to dissolve sugar in hot tea than it is in cold tea. But we're also going to talk about solubility of gases. Okay? dissolving gases in a liquid. So solubility of gases is such that they become less soluble as temperature increases. A practical example to think about for this, think about warm soda. If you've got warm soda, it loses its fizz much more easily than cold soda. So temperature dependence, I want you to be able to think about that qualitatively. Pressure, this only applies to gases. We can't actually increase the solubility of a salt in water by pushing on it, but we can with gases. Okay? And there's an equation here that allows us to think about the solubility of a gas is directly proportional to the concentration of the gas. Remember, partial pressure is a way to measure concentration. And then a constant that we call a Henry's law gas constant. That's just a constant that's specific to a certain gas and to a solvent. But this kind of makes sense, right? The greater the concentration of carbon dioxide gas that you're going to have sitting above your soda, the more fizzy it's going to be. You're going to be able to have more of that gas get into solution. And we can increase the pressure to kind of push it down in there. So lots of qualitative pieces there in our first skill here in this unit to help us think about solubility, solutions, and then the solution process.